Imagine we have a list of numbers, and we want to find the sum of a specific range. Sounds simple, right? We could just look through the numbers and add them up one by one. But here's the problem. What if we had to do this over and over again? If we start from scratch every single time, it becomes incredibly slow. Doing this a million times is just not efficient. So, we came up with a better idea. Instead of calculating on the fly, we add up the numbers ahead of time. We call this a prefix sum. For convenience, let's start our index at 1. Now, to answer a query, we take the prefix sum at the end of our range and subtract the bar we don't need. Just like that, every query now takes a constant number of operations. This is way better than an AE approach. So, prefix sum are cool and intuitive. But before we move on to more advanced data structures, we need to know one key concept. Any integer n can be broken down into a sum of unique powers of 2. Let me show you. Say we start with 1 and 2. We can combine them to make 3. And watch what happens when we bring in 4. By adding 4 to what we already had, we can make every number up to 7. This button continues with 8. It fills in all the gaps up to 15. Because we can always fill in the gaps, any number can be built using powers of 2. Now, let's look at the Sparse Table. In this table, each row covers a range based on a power of 2. I will highlight it for you here. The first row only covers one element each, so we should copy the whole array down. For the next row, we notice that each half of the range is already built in the previous row, so we just combine them. We should keep doing this for every row. Let's try a query. We want a sum from box 1 to box 7. The length is 7. We can just break this into 3 chunks. A length of 4, a length of 2, and a length of 1. But you might wonder, why use Sparse Table when Prefix Sum can already do this better? It is because a Sparse Table can do 2 types of operation, associated and idempotent. Sum is associated because we can group the numbers however we want. But if there is some overlap, it will result in double counting. Finding the minimum is idempotent because overlap don't matter. We can take advantage of this to do a range minimum query. Let's rebuild our table real quick. Let's find the minimum on our earlier range. We pick the largest chunk that fits inside our range. Then we can just overlap 2 chunks to get our answer. Now, every query only takes one minimum operation. But perfect sum and Sparse tables all share the same flaw. If we change just one number in our array, our query becomes wrong. To get the correct result, we have to rebuild the whole thing and run the query again. To solve this problem, we use a data structure called a segment tree. Let's build one. The bottom leaves of the tree are just a copy of our array. Each leaf is one element. Next, we break them up into bigger nodes. We keep doing this until we reach the top root. Now, our tree is done. If our array size is above 2, a tree will be a perfect binary tree. If not, we should add empty nodes and rebuild. Let's find the sum of a range. We start at the top root and go down. If a node is only partly inside our range, we split it and go deeper. If a node is totally outside of our range, we stop and backtrack. When we find a node completely inside our range, we take its sum, and we keep doing this until we cover the whole range. The update operation is much simpler. We just do a binary search to find a node, update it, and then rebuild the branch going back to the root. To show you why this is fast, let's scale the tree up. When we run our query, at each level of the tree, we will visit at most 4 nodes in the worst case, 2 nodes that fit perfectly in the range, and 2 nodes that partially fit, or are completely out of range. So, the maximum number of nodes we will visit is 4 times the height of the tree. This is equivalent to 4 times log base 2 of n, and a log function is really efficient for a huge n. But doing query on a flat array does get old. So, we competitive programmers burn it ourselves by making it harder. We put the problem on a graph, or more specifically, a tree. We want to do 2 things. Find the sum of a path between 2 nodes, and change the value of a node. First, we need to clean up our tree. We start by calculating the size of each subtree. Starting from the top, we look for the biggest branch. We mark these as heavy nodes, and we keep repeating this for the whole tree. Notice how the heavy nodes form long, straight chains down to the bottom. And guess what? We already know how to query on a straight line. Let's look at the path from node 3 to node 7. We can break it down into these 2 heavy paths. A 3 for this path. Now everything is clear. Let's see the algorithm in action. And that's all for this video. See you again next time.